Class, we'll just start our topic of semiconductors, right? So, so we just start with the semiconductor. So you already had information, right? Semiconductors are nothing but the materials whose electrical conductivity lies between the conductor and insulator. You can just see the right. So semiconductors are the materials whose electrical conductivity lies between the conductors and the insulators, and the conductivities of these material is lying between. You can just see the range. Yeah, you can just see the range also. It is found to be 10 power of minus 4 to 10 power of plus 4 Siemens per meter. So the important parameter of a semiconductor, you can just see that there will be two charge carriers. Now, in the conductors, you will find that there is only one charge carrier, but in semiconductor, the charge carriers are two. That is holes and also the electrons. Now we'll just know the concept of holes, right? So as we know that the flow of charge in a given conductor is due to the electrons. Now the extra charge carrier that is coming in the semiconductor is the holes. Now we just have a very quick idea regarding the formation of holes, how holes are formed, or we just say the concept of hole. We are going to learn in today's session, and also we'll learn about carrier concentration of intrinsic semiconductor and also p-n junction diodes and so on. See, in this part, now this property, how the property is shown by the semiconductor, what is the basic parameter by which this property is shown by the semiconductor. What is that property? That it is electrical conductivity is lying between metals and conductors. So they can be determined by the crystal structure bonding, and you already know that the bonding which is taking place in this particular semiconducting materials are due to the covalent bond. So the silicon and germanium, you had information regarding the previous knowledge from your previous knowledge that silicon and germanium are the semiconductors, and also they exhibit the little bit. We'll just move to the chemistry, right? They'll have the SNP sp3 hybridization, right? So here that part is actually an information that a student should understand. So what type of hybridization? When we talk about bonding, so what type of hybridization is taking place in the semiconductors such as silicon and germanium, that is sp3 hybridization. That is for your information sake. Now we'll just start our main topic of the semiconductors. Semiconductors, there are two types of semiconductors, as you know that intrinsic semiconductor, that is also known as pure semiconductor, and also extrinsic semiconductor. Now, when you talk about intrinsic semiconductor, how a student can know that how it is known as intrinsic semiconductor, right? So the naming of the semiconductor is actually dependent on the temperature. So here the temperature plays an important role, which the material can be divided into different with different names. So semiconductor which does not have any kind of impurity, and it will behave as an insulator at 0 Kelvin. So you can just say, so at a 0 Kelvin, it is behaving as an insulator, and it is behaving as a conductor when when you increase the temperature from 0 Kelvin to some Kelvin, Kelvin, uh, at higher temperature, it is known as intrinsic semiconductor. So you can just see that if the given material is at 0 Kelvin, the same material is exhibiting the property of insulator. And if I increase the temperature from 0 Kelvin, right, the same material is acting as a conductor. So you can just say that the semiconductor, depending upon the temperature, the character of that particular material is changing, and sometimes it will act as insulator, and at some temperature, sometimes at a particular temperature it acts as insulator, and you increase the temperature, then it is acting as a conductor. right? So germanium and silicon, you already having the information. They are the fourth group elements, and they are the examples of the intrinsic semiconductor, and they possess a diamond cubic crystalline structure. You know that in the unit 1 we studied about the crystalline structure, and particularly why we have concentrated on cubic crystal structure. Now you can understand that it actually belonging to the semiconductor. We want to study a detail about the semiconductor, and the silicon germanium comes under the category of cubic crystalline structure, right? So this is the information regarding the intrinsic semiconductor. As we move on, so how the bond is formed, right? What is actually valence cell look like, right? In schematical view. Now you can just see this as a silicon atom, and this silicon in the silicon atom you find that these are the valence electrons, right? The neighboring silicon atoms, you can just see as a schematic diagram. So these neighboring crystalline atoms with the other silicon atom, so the one silicon atom is combined with the another silicon atom, then you just see this particular direction, vertical direction. So the bond which is formed between these two neighboring atoms, right, with the electrons which are present in the valence shell, you can just see. So that is called a covalent bond. So hence we just say that there are 4 valence electrons in the uh, valence shell of each silicon atom. When we see the band diagram, right, we just studied in the previous class the origin of energy bands in the solid. So one band is conduction band, another is the valence band, and the basic difference, you can say the gap which is formed between the conduction band and the valence band is nothing but we say that is called the band gap. So here you can just see this the conduction band. In the conduction band, when I increase the temperature from the valence shell, the electron will move to the conduction band, and the empty space. This is the empty space, which is known now. This empty space is known as the hole. So this is happening at when I increase the temperature from 0 Kelvin to the to higher value. So the electrons from the valence band will move to the conduction band. So what is happening here? Again, you can just see this is called the exact, we can say middle way is known as a Fermi energy level. What is the meaning of Fermi energy level? So in the Fermi energy level, the level in below this is completely filled. The level which is above this is completely empty. Now this is called Fermi level, and the gap, whatever you are finding, that gap is known as the energy band gap. So you can just see this. This is the higher value of the valence band. So EV is nothing but the higher value of the valence band, which is represented with EV, and this is the lower value of the conduction band. Therefore, it is represented by AC. So when I say the kinetic, the movement, see, you can know that there is a movement of the electron. Electrons are freely moving. So the kinetic in the conduction band. So the kinetic energy of the electron is given by E minus EC. How sir it is E minus EC? When we just plot a graph in between the distance, you see this particular aspect on the x-axis is taken as the distance. On the y-axis, this is the energy of the electron, and which is given by the total energy of the electron, which is compromising of conduction band, valence band, and the band gap is E, right? So the kinetic energy of the whole is given by EV, the highest value, EV minus E. And the kinetic energy of the electron is given by E minus EC. Clear, everybody? Now, with this, we can just say that the kinetic energy of the electron and the kinetic energy of the kinetic energy of the electron is given by E minus EC, and the kinetic energy of the hole is given by EV minus E. Right now, as we move on, so the carrier concentration, now we'll just go to the concept of carrier concentration. See, we got an information. What is semiconductor? Semiconductor is an element in which the electrical conductivity of an element lies between conductors and the insulator. Here, you can just see this, when we talk about the semiconductor, and depending upon the, what you can say, the semiconductors are being classified into 2 categories. Now, depending upon the structure, right? You can say the crystalline structure and also the bond formation. So they have been classified into two categories. That is intrinsic semiconductor and also extrinsic semiconductor. So intrinsic semiconductors are pure semiconductors. And now we need to, why we are studying about carrier concentration. As you know that in a semiconductor, there are two types of charge carriers, electrons and holes. That should be mathematically evaluated, or we are just verifying mathematically. There is existence of not only the electron as a charge carrier, but also the holes as a charge carrier, which are residing inside the semiconductor. So that is the reason that we are just studying about the carrier concentration in the intrinsic semiconductor. So when a suitable form of energy is supplied to a semiconductors, so the electrons take transition from the valence band to the conduction. Just now we have seen this particular statement with a schematic diagram. So here the electron as it move to the conduction band, so they are free, and the remaining the empty space, which is a positive charge in the valence band, is said to be hole, and this is called the phenomena of Hare hole and the electron generation. So in the intrinsic semiconductor, the number of the electrons, conduction electron, will be equal to the number of holes in the valence. And this is important aspect, right? So in any intrinsic semiconductor, when we talk about intrinsic semiconductor, the number of electrons in the conduction band is equal to the number of holes in the valence band. Why I'm saying it is a holes? It is also known as the vacant size, which is left behind after the electron will move from the valence band to the conduction band. Now we need to calculate this mathematically. So how we are going to calculate it? So now we are calculating the density of electrons, right? So we need to calculate carrier concentration of intrinsic semiconductor. So we need to first of all calculate the number of conduct. You can just see that we want to calculate the number of electrons, conduction electrons, which are present in the conduction band. Then we'll calculate the number of holes which are present in the valence band. So now so you can just see this, how we are going to calculate it. So let us consider the Dn is the number of electrons which are available in the energy interval E and E plus DE in the conduction band. So there will be some change in the energy. The electrons which are residing at the bottom of the conduction band, and also the electrons which are residing at the surface of the conduction band, there will be some, we can say, the variation of energy, and that energy interval we are taking it as E and E plus D in the conduction band. Clear, everybody? So now with this, we are writing that the number of electrons is represented with a small value of, see, this is small dn, right? So which is represented with Z of E, the density of energy states. See, when I talk about electron, right, definitely the electron will have some energy state. So just representing mathematically the number of electrons in the conduction band with Dn, which is equal to the product of the density of energy state, which is represented by Z of E, and this density of energy state is also multiplied with the product of F of E, where F of E is the probability of occupancy of the electron. You can say that there are electrons, right? We cannot know how many electrons are there. Therefore, wherever in mathematics we are not aware of exact thing, we use the probability concept. So that is the reason that we are just writing it, it's F of E, and this is what dE. Now, so n will be, when you just take integration on both sides, this dn will be, you know, that can be there's a small one, and the just I can write it as n. So n is equal to, definitely there will be limits. So EC, as you seen in the diagram, you can see the diagram, right? The lower limit is EC, and the higher value or the top of the band. So this is the lower limit, and this is top of the band. Right? Clear, everybody? So what I've written here, the lower value is EC and the higher value is top. So Z of E into F of E into DE. This is equation number 1. We need to calculate the density of electrons which are present in the conduction band. So where Z of E, DE is the density of energy state in the energy intervals E and E plus D, and F of E is the probability of occupancy of the electron. So the density of energy state, just now I told you, Z of ED is already calculated value is there. So that calculated value is the number of energy state per unit volume, that is Z of E into D is equal to, for this you have to just make a note of it that the density of energy state is given by Z of E, F of E. Z of E into D is given by 4 pi h cube 2m whole to the power of 3 by 2 into e to the power of 1 by 2 into D. Right? So this formula you need to by heart it. That is a density of energy state. There is a derivation, right? How I got this, how we got this Z of E dE. So we are not going into that derivation for now. So we just we need to remember this value of density of energy state. So that is 4 pi h cube into 2m whole to the power of 3 by 2 e to the power of 1 by 2 into d, where m is the mass of the particle and e is the total energy of that particular particle. So here, so z of e dE is equal to 4 pi by h cube. So 2m, so instead of m, what I can write? M suffix e asterisk y, because it is the free electron is free to move anywhere inside the conduction band, either at the bottom of the conduction band, either at the surface of the conduction band. So just it can be represented with me to the power asterisk, right, whole to the power of 3 by 2 e to the power of 1 by 2 into d. Since the energy E start at the bottom of the conduction, you know that E is starting at the bottom of the conduction band. You can just see this. Again, I will show you. See, E is starting from the bottom of the conduction band. So the lower value is EC and the higher value is the top of the band. So what I can do, so he can see the kinetic energy of the electron as it is moving from one end to the another end inside the conduction band. So the kinetic energy of the electron is given by the E minus EC, right? Now, so that is the reason that what I'm doing here, see, I have written E minus EC equal to the power of 1 by 2 into D, right? Understood, everybody? So now this is the density of energy state, mathematical value of formula by which we can calculate the value of density of energy state. Clear? So now now what is f of E? Probability of the occupancy of the electrons in the energy state E is given by f of E. This is a basic formula of the calculating the amount of electrons which are present inside the conduction band. So mathematically it is given by f of E is equal to 1 by 1 plus exponential of E minus EF by KT. Now this is this you need to remember this formula again. So f of E is equal to the occupancy or probability of the electron inside the conduction band can be given by, see, we don't know exactly how many electrons are. So we are using the probability concept here. So f of E is equal to 1 by 1 plus exponential of E minus EF by kT. So for all the possible temperature, E minus EF should be very much greater than kT. Right? Now this particular condition we are using here. So when f of E is equal to E minus EF is very much greater than kT. So what you can say, E minus EF by kT is very much greater than 1. Right? You can see, you can just see this E minus EF is, so I will show you now. The E, you can just see E minus EF right? E minus EF by KT is very much greater than 1, right? So E minus EF by KT from this particular E minus EF by KT is very much greater than 1. So 1 can be neglected. You can just neglect 1 since the 1 value is very, very less when compared with E minus EF by KT. So therefore, I've written here E minus exponential of E minus EF by KT. So f of E value, so this is in the denominator. So when it comes to the numerator, so E minus EF by KT, so the negative sign will come. Or else you can write that f of E is equal to exponential of EF minus E by KT, right? So understood, everyone? What I've written now, f of E value I got exponential of EF minus E by KT. Now substituting this value of Z of E, F of E in the equation 1. So what is our equation 1? N is equal to integration of EC top, the maximum limit is the upper part of the band. So you can say it's top of the band, or you can just write it as infinity, right? So Z of E into F of E into D. So what I can write, n is equal to EC by infinity. Z of E value, we just now we got 4 by h cube 2 me asterisk whole to the power of 3 by 2. So f of E value just now we got exponential of and E minus EC by, this is the kinetic energy of the electron. So exponential of EF minus E by kBT into dE. Right. So now this particular part will come out this particular integration. So EC by infinity integration lower limit upper limit E minus EC whole to the power 1 by 2. Now exponential of EF minus EF by kBT into dE. Right. So now when I just write this exponential of EF minus E by kBT, I'm just taking out from the inside the integration. It is in this particular right value. So what I'm writing here 4 by h cube to me asterisk exponential of EF by KT. I'm taking out E minus EC whole to the power of 1 by 2. So what is remaining inside it? The exponential of minus E by KT into D. See, in the E exponential means E to the power. So E to the power of, see, I can write exponential of EF minus E by KT, and also it has exponential of EF by KT and exponential of minus E by KT. So when you just write it in the product form, so I'm just taking that exponential of EF by KT outside. Clear, everybody? Now, so now see, now we want to solve this integration equation. How we are going to solve? By using this concept. Let us consider E minus EC is equal to X and E is equal to EC plus X. And here the differentiation of DE, instead of D, what I can write here, since you considered X, so dx, so n is equal to 4 by h cube 2 me as equal to the power of 3 by 2 exponential of EF by KT 0 to infinity. Now the limits also change, right? So what is wherever you find this value, you can just substitute that. You can see the limit is what? EC. Lower limit is EC, and here the upper limit is infinity. So here, as you are considering the function, so the limits will also change, and the limits now will be, lower limit was EC. So I just substitute here instead of EC minus EC is 0, X's value is 0. Therefore, I will written 0 here, right? Instead of E, we need to substitute the limit. So if it is lower limit, that is EC. So when the lower limit is EC, so I have instead of E, I have written here EC. So EC minus EC is equal to X. So X is equal to 0. Clear, everybody? Now here again I need to substitute the energy of the upper limit. So infinity minus EC is equal to X. So X is equal to infinity. So I have written here 0 to infinity E minus EC whole to the power of 1 by 2 exponential of minus E by KT into D. So n is equal to 4 by h cube 2 me as equal to the power of 3 by 2 exponential of EF by KT integration of 0 to infinity. So in E minus ECs, you can know that is what you are aware of this X. So X to the power of 1 by 2 exponential of minus, see E. What is E here? EC plus X. So instead of E, you can just see this. E is equal to EC plus X. So minus of E. So minus, I'll take it outside. So I can write EC plus X minus of EC plus X by KT into dx. Clear, everybody? Now here, now you can just, again I told you that exponential part. So EF minus EC by KT I'm taking. So exponential of EF minus EC by KT outside. So what is remaining here? Exponential of minus X minus will go inside. So minus X by KT into dx. Now this is equation number 3. Now we know that the part of this value integration of 0 to infinity x x to the power of 1 by 2 into exponential of minus x, it can be written as root pi by 2. That is called gamma function. So this in the mathematics, if you are not aware of this, you can just ask your mathematics sir. This is actually called gamma function. What is gamma function? The integration is having a limit of 0 to infinity and x to the power of 1 by 2 exponential of minus x by kt into d. This can be written as root pi by 2. So I'm writing here, substituting this equation number 3. So n is equal to 4 pi h cube 2 me asterisk outside the integration part 3 by 2 exponential of ef minus ct, and this is what root pi by 2, right? So now so this 2 is there inside 3 by 2, and outside you will find 4, and here also you'll find 2 here in that. So 2 ones are 2 2s are. So what is it? 2 pi me asterisk kt whole to the power of 3 by 2 h square into exponential of ef minus ec by kt. So you can just see this KT, EF minus EC by KT. So this is KT I'm taken inside to here to pi, and pi root pi is also taken inside. You can see this. This is equation which says that the number of electrons per unit volume of the given semiconductor. So in this given semiconductor, we have just calculated the number of electrons per unit volume of the given material. In the same way, we can calculate the number of holes per unit volume of the given material. This part will be same. Here, this part will be changed, and instead of EC, you'll find EV here. EF will also change. You can see